Unit 5 Thermodynamics. Objectives. After studying this unit, you will be able to explain the terms system and surroundings, discriminate between closed, open, and isolated systems, explain internal energy, work, and heat, state first law of thermodynamics and express it mathematically, calculate energy changes as work and heat contributions in chemical systems, explain state functions U, H, correlate delta U and delta H, measure experimentally delta U and delta H, define standard states for delta H, calculate enthalpy changes for various types of reactions, state and apply Hess law of constant heat summation, differentiate between extensive and intensive properties, define spontaneous and non-spontaneous processes, explain entropy as a thermodynamic state function and apply it for spontaneity, explain Gibbs energy change delta G and establish relationship between delta G and spontaneity, delta G and equilibrium constant. It is only the physical theory of universal content concerning which I am convinced that, within the framework of the applicability of its basic concepts, it will never be overthrown. Albert Einstein. Chemical energy stored by molecules can be released as heat during chemical reactions when a fuel like methane, cooking gas, or coal burns in air. The chemical energy may also be used to do mechanical work when a fuel burns in an engine, or to provide electrical energy through a galvanic cell like dry cell. Thus, various forms of energy are interrelated, and under certain conditions, these may be transformed from one form into another. The study of these energy transformations forms the subject matter of thermodynamics. The laws of thermodynamics deal with energy changes of macroscopic systems involving a large number of molecules rather than microscopic systems containing a few molecules. Thermodynamics is not concerned about how and at what rate these energy transformations are carried out, but is based on initial and final states of a system undergoing the change. Laws of thermodynamics apply only when a system is in equilibrium or moves from one equilibrium state to another equilibrium state. Macroscopic properties like pressure and temperature do not change with time for a system in equilibrium state. In this unit, we would like to answer some of the important questions through thermodynamics like: how do we determine the energy changes involved in a chemical reaction or process? Will it occur or not? What drives a chemical reaction or process? To what extent do the chemical reactions proceed? 5.1 Thermodynamic Terms. We are interested in chemical reactions and the energy changes accompanying them. For this, we need to know certain thermodynamic terms. These are discussed below. 5.1.1 The system and the surroundings. A system in thermodynamics refers to that part of universe in which observations are made, and remaining universe constitutes the surroundings. The surroundings include everything other than the system. System and the surroundings together constitute the universe. The universe equals the system plus the surroundings. However, the entire universe other than the system is not affected by the changes taking place in the system. Therefore, for all practical purposes, the surroundings are that portion of the remaining universe which can interact with the system. Usually, the region of space in the neighborhood of the system constitutes its surroundings. For example, if we are studying the reaction between two substances A and B kept in a beaker, the beaker containing the reaction mixture is the system, and the room where the beaker is kept is the surroundings. Figure 5.1. Note that the system may be defined by physical boundaries like beaker or test tube, or the system may simply be defined by a set of Cartesian coordinates specifying a particular volume in space. It is necessary to think of the system as separated from the surroundings by some sort of wall, which may be real or imaginary. The wall that separates the system from the surroundings is called boundary. This is designed to allow us to control and keep track of all movements of matter and energy in or out of the system. 5.1.2 Types of the system. We further classify the systems according to the movements of matter and energy in or out of the system. 1. Open system. In an open system, there is exchange of energy and matter between system and surroundings. Figure 5.2a. The presence of reactants in an open beaker is an example of an open system. We could have taken only the reactants as system, then walls of the beakers will act as boundary. Here, the boundary is an imaginary surface enclosing the beaker and the reactants. 2. Closed system. In a closed system, there is no exchange of matter, but exchange of energy is possible between system and the surroundings. Figure 5.2b. The presence of reactants in a closed vessel made of conducting material, example copper or steel, is an example of a closed system. 3. Isolated system. In an isolated system, there is no exchange of energy or matter between the system and the surroundings. Figure 5.2c. The presence of reactants in a thermos flask or any other closed insulated vessel is an example of an isolated system. 5.1.3 The state of the system. The system must be described in order to make any useful calculations by specifying quantitatively each of the properties such as its pressure P, volume V, and temperature T, as well as the composition of the system. We need to describe the system by specifying it before and after the change. You would recall from your physics course that the state of a system in mechanics is completely specified at a given instant of time by the position and velocity of each mass point of the system. In thermodynamics, a different and much simpler concept of the state of a system is introduced. It does not need detailed knowledge of motion of each particle because we deal with average measurable properties of the system. We specify the state of the system by state functions or state variables. The state of a thermodynamic system is described by its measurable or macroscopic bulk properties. We can describe the state of a gas by quoting its pressure P, volume V, temperature T, amount N, etc. Variables like P, V, T are called state variables or state functions because their values depend only on the state of the system and not on how it is reached. In order to completely define the state of a system, it is not necessary to define all the properties of the system, as only a certain number of properties can be varied independently. This number depends on the nature of the system. Once these minimum number of macroscopic properties are fixed, others automatically have definite values. The state of the surroundings can never be completely specified. Fortunately, it is not necessary to do so. 5.1.4 The internal energy as a state function. When we talk about a chemical system losing or gaining energy, we need to introduce a quantity which represents the total energy of the system. It may be chemical, electrical, mechanical, or any other type of energy you may think of. The sum of all these is the energy of the system. In thermodynamics, we call it the internal energy U of the system, which may change when heat passes into or out of the system, work is done on or by the system, matter enters or leaves the system. These systems are classified accordingly as you have already studied in section 5.1.2. A. Work. Let us first examine a change in internal energy by doing work. We take a system containing some quantity of water in a thermos flask or in an insulated beaker. This would not allow exchange of heat between the system and surroundings through its boundary, and we call this type of system as adiabatic. The manner in which the state of such a system may be changed will be called adiabatic process. Adiabatic process is a process in which there is no transfer of heat between the system and surroundings. Here, the wall separating the system and the surroundings is called the adiabatic wall. Figure 5.3. Let us bring the change in the internal energy of the system by doing some work on it. Let us call the initial state of the system as state A and its temperature as TA. Let the internal energy of the system in state A be called UA. We can change the state of the system in two different ways. One way, we do some mechanical work, say 1 kilojoules, by rotating a set of small paddles and thereby churning water. Let the new state be called B state and its temperature as TB. It is found that TB greater than TA and the change in temperature delta T equals TB minus TA. Let the internal energy of the system in state B be UB and the change in internal energy delta U equals UB minus UA. Second way, we now do an equal amount, that is 1 kilojoules, electrical work with the help of an immersion rod and note down the temperature change. We find that the change in temperature is same as in the earlier case, say TB minus TA. In fact, the experiments in the above manner were done by J.P. Joule between 1840 to 50, and he was able to show that a given amount of work done on the system, no matter how it was done, irrespective of path, produced the same change of state as measured by the change in the temperature of the system. So it seems appropriate to define a quantity, the internal energy U, whose value is characteristic of the state of a system, whereby the adiabatic work WAD required to bring about a change of state is equal to the difference between the value of U in one state and that in another state, delta U, that is, delta U equals U2 minus U1 equals WAD. Therefore, internal energy U of the system is a state function. By conventions of IUPAC in chemical thermodynamics, the positive sign expresses that WAD is positive when work is done on the system and the internal energy of the system increases. Similarly, if the work is done by the system, WAD will be negative because internal energy of the system decreases. Can you name some other familiar state functions? Some of the other familiar state functions are V, P, and T. For example, if we bring a change in temperature of the system from 25 degrees Celsius to 35 degrees Celsius, the change in temperature is 35 degrees Celsius minus 25 degrees Celsius equals plus 10 degrees Celsius. Whether we go straight up to 35 degrees Celsius or cool the system for a few degrees, then take the system to the final temperature. Thus, T is a state function and the change of temperature is independent of the route taken. Volume of water in a pond, for example, is a state function because change in volume of its water is independent of the route by which water is filled in the pond, either by rain or by tube well or by both. B. Heat. We can also change the internal energy of a system by transfer of heat from the surroundings to the system or vice versa without expenditure of work. This exchange of energy, which is a result of temperature difference, is called heat Q. Let us consider bringing about the same change in temperature, the same initial and final states as before in section 5.1.4a by transfer of heat through thermally conducting walls instead of adiabatic walls. Figure 5.4. We take water at temperature TA in a container having thermally conducting walls, say made up of copper and enclose it in a huge heat reservoir at temperature Tb. The heat absorbed by the system, water, Q, can be measured in terms of temperature difference Tb minus Ta. In this case, change in internal energy delta U equals Q when no work is done at constant volume. By conventions of IUPAC in chemical thermodynamics, the Q is positive when heat is transferred from the surroundings to the system and the internal energy of the system increases, and Q is negative when heat is transferred from system to the surroundings, resulting in decrease of the internal energy of the system. C. The general case. Let us consider the general case in which a change of state is brought about both by doing work and by transfer of heat. We write change in internal energy for this case as delta U equals Q plus W, equation 5.1. For a given change of state, Q and W can vary depending on how the change is carried out. However, Q plus W equals delta U will depend only on initial and final state. It will be independent of the way the change is carried out. If there is no transfer of energy as heat or as work isolated system, that is, if W is equal to 0 and Q is equal to 0, then delta U equals 0. The equation 5.1, that is, delta U equals Q plus W, is mathematical statement of the first law of thermodynamics, which states that the energy of an isolated system is constant. It is commonly stated as the law of conservation of energy, that is, energy can neither be created nor be destroyed. Note, there is considerable difference between the character of the thermodynamic property energy and that of a mechanical property such as volume. We can specify an unambiguous absolute value for volume of a system in a particular state, but not the absolute value of internal energy. However, we can measure only the changes in the internal energy delta U of the system. Problem 5.1. Express the change in internal energy of a system when 1. No heat is absorbed by the system from the surroundings, but work W is done on the system. What type of wall does the system have? 2. No work is done on the system, but Q amount of heat is taken out from the system and given to the surroundings. What type of wall does the system have? 3. W amount of work is done by the system and Q amount of heat is supplied to the system. What type of system would it be? Solution. 1. Delta U equals WAD, wall is adiabatic. 2. Delta U equals minus Q, thermally conducting walls. 3. Delta U equals Q minus W, closed system. 5.2. Applications. Many chemical reactions involve the generation of gases capable of doing mechanical work or the generation of heat. It is important for us to quantify these changes and relate them to the changes in the internal energy. Let's see how. 5.2.1 Work. First of all, let us concentrate on the nature of work a system can do. We will consider only mechanical work, that is, pressure-volume work. For understanding pressure-volume work, let's consider a cylinder which contains 1 mole of an ideal gas fitted with a frictionless piston. Total volume of the gas is Vi and pressure of the gas inside is P. If external pressure is Px, which is greater than P, piston is moved inward till the pressure inside becomes equal to Px. Let this change be achieved in a single step and the final volume be Vf. During this compression, suppose piston moves a distance L and its cross-sectional area of the piston is A. figure 5.5a. Then volume change equals L into A equals delta V equals Vf minus Vi. We also know pressure equals force divided by area. Therefore, force on the piston equals Px into A. If W is the work done on the system by movement of the piston, then W is equal to force into distance equals Pex into A into L equals Pex into minus delta V equals minus Pex into delta V equals minus Pex into Vf minus Vi. Equation 5.2. The negative sign of this expression is required to obtain conventional sign for W, which will be positive. It indicates that in case of compression, work is done on the system. Here, Vf minus Vi will be negative and negative multiplied by negative will be positive. Hence, the sign obtained for the work will be positive. If the pressure is not constant at every stage of compression but changes in number of finite steps, work done on the gas will be summed over all the steps and will be equal to minus sigma P into delta V, figure 5.5b. If the pressure is not constant but changes during the process such that it is always infinitesimally greater than the pressure of the gas, then at each stage of compression, the volume decreases by an infinitesimal amount dV. In such a case, we can calculate the work done on the gas by the relation W is equal to minus integral Vi to Vf Pex dV, equation 5.3. Here, Pex at each stage is equal to Pin plus dP in case of compression, figure 5.5c. In an expansion process under similar conditions, the external pressure is always less than the pressure of the system, that is, Pex equals Pin minus dP. In general case, we can write Pex equals Pin plus or minus dP. Such processes are called reversible processes. A process or change is said to be reversible if a change is brought out in such a way that the process could at any moment be reversed by an infinitesimal change. A reversible process proceeds infinitely slowly by a series of equilibrium states such that system and the surroundings are always in near equilibrium with each other. Processes other than reversible processes are known as irreversible processes. In chemistry, we face problems that can be solved if we relate the work term to the internal pressure of the system. We can relate work to internal pressure of the system under reversible conditions by writing equation 5.3 as follows. WREV equals minus integral from Vi to Vf Pex dV equals minus integral Vi to Vf Pin plus or minus dP into dV. Since dP into dV is very small, we can write WREV equals minus integral from Vi to Vf Pin dV, equation 5.4. Now the pressure of the gas Pin, which we can write as P now, can be expressed in terms of its volume through gas equation. For n mole of an ideal gas, that is, PV is equal to N into R into T, implies P is equal to N into R into T divided by V. Therefore, at constant temperature isothermal process, WREV equals minus integral ranging from Vi to Vf N into R into T into dV divided by V equals minus N into R into T ln Vf divided by Vi equals minus 2.303 N into R into T log Vf divided by Vi, equation 5.5. Free expansion. Expansion of a gas in vacuum Pex is equal to 0 is called free expansion. No work is done during free expansion of an ideal gas, whether the process is reversible or irreversible. Equation 5.2 and 5.3. Now we can write equation 5.1 in number of ways depending on the type of processes. Let us substitute W is equal to minus Pex into delta V, equation 5.2 in equation 5.1, and we get delta U equals Q minus Pex into delta V. If a process is carried out at constant volume, delta V equals 0, then delta U equals QV. The subscript V in QV denotes that heat is supplied at constant volume. Isothermal and free expansion of an ideal gas. For isothermal, T equals constant. Expansion of an ideal gas in vacuum, W is equal to 0 since Pex is equal to 0. Also, Joule determined experimentally that Q is equal to 0, therefore delta U equals 0. Equation 5.1, delta U equals Q plus W can be expressed for isothermal irreversible and reversible changes as follows. 1. For isothermal irreversible change, Q equals minus W equals Pex into Vf minus Vi. 2. For isothermal reversible change, Q equals minus W equals N into R into T ln Vf divided by Vi equals 2.303 into N into R into T log of Vf divided by Vi. For adiabatic change, Q is equal to 0, delta U equals WAD. Problem 5.2. 2 liters of an ideal gas at a pressure of 10 atm expands isothermally at 25 degrees Celsius into a vacuum until its total volume is 10 liters. How much heat is absorbed and how much work is done in the expansion? Solution. We have Q equals minus W equals Pex into 10 minus 2 equals 0 into 8 equals 0. No work is done, no heat is absorbed. Problem 5.3. Consider the same expansion, but this time against a constant external pressure of 1 atm. Solution. We have Q equals minus W equals Pex into 8 equals 8 liter atm. Problem 5.4. Consider the expansion given in problem 5.2 for 1 mole of an ideal gas conducted reversibly. Solution. We have Q equals minus W equals 2.303 into N into R into T into log Vf divided by Vs equals 2.303 into 1 into 0.8206 into 298 into log of 10 divided by 2 equals 2.303 into 0.8206 into 298 into log 5 equals 2.303 into 0.8206 into 298 into 0.6990 equals 393.66 L atm. 5.2.2 Enthalpy H. A useful new state function. We know that the heat absorbed at constant volume is equal to change in the internal energy, that is delta U equals QV. But most of the chemical reactions are carried out not at constant volume but in flasks or test tubes under constant atmospheric pressure. We need to define another state function which may be suitable under these conditions. We may write equation 5.1 as delta U equals Qp minus P into delta V at constant pressure, where Qp is heat absorbed by the system and minus P delta V represents expansion work done by the system. Let us represent the initial state by subscript 1 and final state by 2. We can rewrite the above equation as U2 minus U1 equals Qp minus P into V2 minus V1. On rearranging, we get Qp equals U2 plus PV2 minus U1 plus PV1. Equation 5.6. Now we can define another thermodynamic function, the enthalpy H, Greek word enthalpian to warm or heat content as H is equal to U plus P into V. Equation 5.7. So equation 5.6 becomes QP equals H2 minus H1 equals delta H. Although Q is a path-dependent function, H is a state function because it depends on U, P and V, all of which are state functions. Therefore, delta H is independent of path. Hence, QP is also independent of path. For finite changes at constant pressure, we can write equation 5.7 as delta H equals delta U plus delta P into V. Since P is constant, we can write delta H is equal to delta U plus P into delta V. Equation 5.8. It is important to note that when heat is absorbed by the system at constant pressure, we are actually measuring changes in the enthalpy. Remember, delta H is equal to QP, heat absorbed by the system at constant pressure. Delta H is negative for exothermic reactions which evolve heat during the reaction, and delta H is positive for endothermic reactions which absorb heat from the surroundings. At constant volume, delta V equals 0, delta U equals QV. Therefore, equation 5.8 becomes delta H is equal to delta U equals QV. The difference between delta H and delta U is not usually significant for systems consisting of only solids and or liquids. Solids and liquids do not suffer any significant volume changes upon heating. The difference, however, becomes significant when gases are involved. Let us consider a reaction involving gases. If VA is the total volume of the gaseous reactants, VB is the total volume of the gaseous products, Na is the number of moles of gaseous reactants, and Nb is the number of moles of the gaseous products, all at constant pressure and temperature, then using the ideal gas law, we write P into Va equals Na into R into T, and PVB equals Nb into R into T. Thus, P into Vb minus P into Va equals Nb into R into T minus Na into R into T equals Nb minus Na into R into T, or P into Vb minus Va equals Nb minus Na into R into T, or P into delta V equals delta Ng into R into T, equation 5.9. Here, delta Ng refers to the number of moles of gaseous products minus the number of moles of gaseous reactants. Substituting the value of P into delta V from equation 5.9 in equation 5.8, we get delta H equals delta U plus delta Ng into R into T. Equation 5.10. The equation 5.10 is useful for calculating delta H from delta U and vice versa. Problem 5.5. If water vapor is assumed to be a perfect gas, molar enthalpy change for vaporization of 1 mole of water at 1 bar and 100 degrees Celsius is 41 kilojoules per mole. Calculate the internal energy change when 1 mole of water is vaporized at 1 bar pressure and 100 degrees Celsius. Solution. 1. The change H2O liquid to H2O gas, delta H equals delta U plus delta Ng into R into T, or delta U equals delta H minus delta Ng into R into T. Substituting the values, we get Delta U equals 41 kilojoules per mole minus 1 into 8.3 joules per mole per K into 373 K equals 41 kilojoules per mole minus 3.096 kilojoules per mole equals 37.904 kilojoules per mole. B. Extensive and intensive properties. In thermodynamics, a distinction is made between extensive properties and intensive properties. An extensive property is a property whose value depends on the quantity or size of matter present in the system. For example, mass, volume, internal energy, enthalpy, heat capacity, etc. are extensive properties. Those properties which do not depend on the quantity or size of matter present are known as intensive properties. For example, temperature, density, pressure, etc. are intensive properties. A molar property chi m is the value of an extensive property chi of the system for 1 mole of the substance. If n is the amount of matter, chi m equals chi divided by n is independent of the amount of matter. Other examples are molar volume Vm and molar heat capacity Cm. Let us understand the distinction between extensive and intensive properties by considering a gas enclosed in a container of volume V and at temperature T. Figure 5.6a. Let us make a partition such that the volume is halved. Each part, figure 5.6b, now has 1/2 of the original volume V divided by 2. But the temperature will still remain the same, that is T. It is clear that volume is an extensive property and temperature is an intensive property. C. Heat capacity. In this subsection, let us see how to measure heat transferred to a system. This heat appears as a rise in temperature of the system in case of heat absorbed by the system. The increase of temperature is proportional to the heat transferred. Q is equal to coef into delta T. The magnitude of the coefficient depends on the size, composition and nature of the system. We can also write it as Q is equal to C into delta T. The coefficient C is called the heat capacity. Thus, we can measure the heat supplied by monitoring the temperature rise, provided we know the heat capacity. When C is large, a given amount of heat results in only a small temperature rise. Water has a large heat capacity, that is, a lot of energy is needed to raise its temperature. C is directly proportional to amount of substance. The molar heat capacity of a substance Cm equals C divided by N is the heat capacity for 1 mole of the substance and is the quantity of heat needed to raise the temperature of 1 mole by 1 degree Celsius or 1 Kelvin. Specific heat, also called specific heat capacity, is the quantity of heat required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius or 1 Kelvin. For finding out the heat Q required to raise the temperatures of a sample, we multiply the specific heat of the substance C by the mass m and temperature change delta T as Q equals small c into m into delta T equals capital C into delta T, equation 5.11. D. The relationship between Cp and Cv for an ideal gas. At constant volume, the heat capacity capital C is denoted by Cv, and at constant pressure this is denoted by Cp. Let us find the relationship between the two. We can write equation for heat Q at constant volume as QV equals CV into delta T equals delta U at constant pressure as QP equals Cp into delta T equals delta H. The difference between Cp and Cv can be derived for an ideal gas as, for a mole of an ideal gas, delta H equals delta U plus delta P into V equals delta U plus delta R into T equals delta U plus R into delta T. Therefore, delta H equals delta U plus R into delta T, equation 5.12. On putting the values of delta H and delta U, we have Cp into delta T equals Cv into delta T plus R into delta T. Cp equals Cv plus R. Cp minus Cv equals R, equation 5.13. 5.3. Measurement of delta U and delta H, calorimetry. We can measure energy changes associated with chemical or physical processes by an experimental technique called calorimetry. In calorimetry, the process is carried out in a vessel called calorimeter, which is immersed in a known volume of a liquid. Knowing the heat capacity of the liquid in which calorimeter is immersed and the heat capacity of calorimeter, it is possible to determine the heat evolved in the process by measuring temperature changes. Measurements are made under two different conditions. 1. At constant volume QV. 2. At constant pressure QP. A. Delta U measurements. For chemical reactions, heat absorbed at constant volume is measured in a bomb calorimeter, figure 5.7. Here, a steel vessel, the bomb, is immersed in a water bath. The whole device is called calorimeter. The steel vessel is immersed in water bath to ensure that no heat is lost to the surroundings. A combustible substance is burned in pure dioxygen supplied in the steel bomb. Heat evolved during the reaction is transferred to the water around the bomb and its temperature is monitored. Since the bomb calorimeter is sealed, its volume does not change, that is, the energy changes associated with reactions are measured at constant volume. Under these conditions, no work is done as the reaction is carried out at constant volume in the bomb calorimeter. Even for reactions involving gases, there is no work done as delta V equals 0. Temperature change of the calorimeter produced by the completed reaction is then converted to QV by using the known heat capacity of the calorimeter with the help of equation 5.11. B. Delta H measurements. Measurement of heat change at constant pressure, generally under atmospheric pressure, can be done in a calorimeter shown in figure 5.8. We know that delta H equals QP at constant P and therefore heat absorbed or evolved QP at constant pressure is also called the heat of reaction or enthalpy of reaction delta RH. In an exothermic reaction, heat is evolved and system loses heat to the surroundings. Therefore, QP will be negative and delta RH will also be negative. Similarly, in an endothermic reaction, heat is absorbed, QP is positive and delta RH will be positive. Problem 5.6. 1 gram of graphite is burnt in a bomb calorimeter in excess of oxygen at 298 K and 1 atmospheric pressure according to the equation C graphite plus O2 gas gives CO2 gas. During the reaction, temperature rises from 298 K to 299 K. If the heat capacity of the bomb calorimeter is 20.7 kilojoules per K, what is the enthalpy change for the above reaction at 298 K and 1 atm? Solution. Suppose Q is the quantity of heat from the reaction mixture and CV is the heat capacity of the calorimeter. Then the quantity of heat absorbed by the calorimeter Q equals CV into delta T. Quantity of heat from the reaction will have the same magnitude but opposite sign because the heat lost by the system reaction mixture is equal to the heat gained by the calorimeter. Q equals minus CV into delta T equals minus 20.7 kJ per K into 299 minus 298 K equals minus 20.7 kJ. Here, negative sign indicates the exothermic nature of the reaction. Thus, delta U for the combustion of the 1 gram of graphite equals minus 20.7 kJ per capital K. For combustion of 1 mole of graphite equals 12 grams per mole into minus 20.7 kJ divided by 1 gram equals minus 2.48 into 10 squared kJ per mole. Since delta Ng equals 0, delta H equals delta U equals minus 2.48 into 10 squared kJ per mole. 5.4. Enthalpy change, delta RH of a reaction, reaction enthalpy. In a chemical reaction, reactants are converted into products and is represented by reactants to products. The enthalpy change accompanying a reaction is called the reaction enthalpy. The enthalpy change of a chemical reaction is given by the symbol delta RH. Delta RH equals sum of enthalpies of products minus sum of enthalpies of reactants equals sigma I AI H products minus sigma I BI H reactants. Equation 5.14. Here, symbol sigma is used for summation and AI and BI are the stoichiometric coefficients of the products and reactants respectively in the balanced chemical equation. For example, for the reaction CH4 gas plus 2O2 gas giving CO2 gas plus 2H2O liquid, delta RH equals sigma I AI H products minus sigma I BI H reactants equals HM CO2G plus 2HM H2OL minus HM CH4G plus 2HM O2G, where HM is the molar enthalpy. Enthalpy change is a very useful quantity. Knowledge of this quantity is required when one needs to plan the heating or cooling required to maintain an industrial chemical reaction at constant temperature. It is also required to calculate temperature dependence of equilibrium constant. A. Standard enthalpy of reactions. Enthalpy of a reaction depends on the conditions under which a reaction is carried out. It is therefore necessary that we must specify some standard conditions. The standard enthalpy of reaction is the enthalpy change for a reaction when all the participating substances are in their standard states. The standard state of a substance at a specified temperature is its pure form at 1 bar. For example, The standard state of liquid ethanol at 298 K is pure liquid ethanol at 1 bar. Standard state of solid iron at 500 K is pure iron at 1 bar. Usually data are taken at 298 K. Standard conditions are denoted by adding the superscript to the symbol delta H, for example delta H superscript. B. Enthalpy changes during phase transformations. Phase transformations also involve energy changes. Ice, for example, requires heat for melting. Normally, this melting takes place at constant pressure, atmospheric pressure, and during phase change, temperature remains constant at 273 K. H2O solid gives H2O liquid. Delta FUS H superscript equals 6 kJ per mole. Here, delta FUS H superscript is enthalpy of fusion in standard state. If water freezes, then process is reversed and equal amount of heat is given off to the surroundings. The enthalpy change that accompanies melting of 1 mole of a solid substance in standard state is called standard enthalpy of fusion or molar enthalpy of fusion, delta FUS H superscript. Melting of a solid is endothermic, so all enthalpies of fusion are positive. Water requires heat for evaporation. At constant temperature of its boiling point Tb and at constant pressure, H2O liquid becomes H2O gas. Delta VAPH equals plus 40.79 kJ per mole. Delta VAPH is the standard enthalpy of vaporization. Amount of heat required to vaporize 1 mole of a liquid at constant temperature and under standard pressure 1 bar is called its standard enthalpy of vaporization or molar enthalpy of vaporization, delta VAPH. Sublimation is direct conversion of a solid into its vapor. Solid CO2 or dry ice sublimes at 195 K with delta SUBH superscript equals 25.2 kJ per mole. Naphthalene sublimes slowly, and for this, delta SUBH superscript equals 73 kilojoules per mole. Standard enthalpy of sublimation, delta SUBH superscript, is the change in enthalpy when 1 mole of a solid substance sublimes at a constant temperature and under standard pressure 1 bar. The magnitude of the enthalpy change depends on the strength of the intermolecular interactions in the substance undergoing the phase transformations. For example, the strong hydrogen bonds between water molecules hold them tightly in liquid phase. For an organic liquid such as acetone, the intermolecular dipole-dipole interactions are significantly weaker. Thus, it requires less heat to vaporize 1 mole of acetone than it does to vaporize 1 mole of water. Table 5.1 gives values of standard enthalpy changes of fusion and vaporization for some substances. Problem 5.7. A swimmer coming out from a pool is covered with a film of water weighing about 18 grams. How much heat must be supplied to evaporate this water at 298 K? Calculate the internal energy of vaporization at 298 K. Delta VAPH for water at 298 K equals 44.01 kilojoules per mole. Solution. We can represent the process of evaporation as H2O liquid 1 mole vaporizes to H2O gas 1 mole. Number of moles in 18 grams of H2O liquid is equal to 18G divided by 18G per mole equals 1 mole. Heat supplied to evaporate 18 grams water at 298 K equals N into delta VAPH equals 1 mole into 44.01 kilojoules per mole equals 44.01 kilojoules, assuming steam behaving as an ideal gas. Delta VAPU equals delta VAPH minus P into delta V equals delta VAPH minus delta NG into R into T. Delta VAPHV minus delta NG into RT equals 44.01 kJ equals minus 1 into 8.314 joules per K per mole into 298 K into 10 raised to minus 3 kJ per J. Delta VAP UV equals 44.01 kJ minus 2.48 kJ equals 41.53 kJ. Problem 5.8. Assuming the water vapor to be a perfect gas, calculate the internal energy change when 1 mole of water at 100 degrees Celsius and 1 bar pressure is converted to ice at 0 degrees Celsius. Given the enthalpy of fusion of ice is 6 kilojoules per mole, heat capacity of water is 4.2 joules per gram degree Celsius. The change takes place as follows. Step 1. 1 mole H2O, L 100 degrees Celsius, to 1 mole L 0 degrees Celsius, enthalpy change delta H1. Step 2. 1 mole H2O, L 0 degrees Celsius to 1 mole H2O, S 0 degrees Celsius, enthalpy change delta H2. Total enthalpy change will be delta H equals delta H1 plus delta H2. Delta H1 equals minus 18 into 4.2 into 100 joules per mole equals minus 7560 joules per mole equals minus 7.56 kilojoules per mole. Delta H2 equals minus 6 kilojoules per mole. Therefore, delta H equals minus 7.56 kilojoules per mole plus minus 6 kilojoules per mole equals minus 13.56 kilojoules per mole. There is negligible change in the volume during the change from liquid to solid state. Therefore, P into delta V equals delta Ng into RT equals 0. Delta H equals delta U equals minus 13.56 kilojoules per mole. C. Standard enthalpy of formation. The standard enthalpy change for the formation of 1 mole of a compound from its elements in their most stable states of aggregation, also known as reference states, is called standard molar enthalpy of formation. Its symbol is delta FH, where the subscript F indicates that 1 mole of the compound in question has been formed in its standard state from its elements in their most stable states of aggregation. The reference state of an element is its most stable state of aggregation at 25 degrees Celsius and 1 bar pressure. For example, the reference state of dihydrogen is H2 gas and those of dioxygen, carbon and sulfur are O2 gas, C graphite and S rhombic respectively. Some reactions with standard molar enthalpies of formation are as follows. H2 gas plus half O2 gas gives H2O liquid. Delta FH equals minus 285.8 kilojoules per mole. C graphite S plus 2H2 gas gives CH4 gas. Delta FH equals minus 74.81 kilojoules per mole. 2C graphite S plus 3H2 gas plus half O2 gas gives C2H5OH liquid. Delta FH equals minus 277.7 kilojoules per mole. It is important to understand that a standard molar enthalpy of formation, delta FH, is just a special case of delta RH, where 1 mole of a compound is formed from its constituent elements, as in the above 3 equations, where 1 mole of each water, methane, and ethanol is formed. In contrast, the enthalpy change for an exothermic reaction, CaO solid plus CO2 gas giving CaCO3S, delta RH equals minus 178.3 kilojoules per mole, is not an enthalpy of formation of calcium carbonate, since calcium carbonate has been formed from other compounds and not from its constituent elements. Also, for the reaction given below, enthalpy change is not standard enthalpy of formation, delta FH for HBr gas. H2 gas plus Br2 liquid gives 2HBr gas. Delta RH equals minus 178.3 kilojoules per mole. Here, 2 moles instead of 1 mole of the product is formed from the elements, that is, delta RH equals 2 into delta FH. Therefore, by dividing all coefficients in the balanced equation by 2, expression for enthalpy of formation of HBr gas is written as half H2 gas plus half Br2 liquid gives HBr gas. Delta FH equals minus 36.4 kilojoules per mole. Standard enthalpies of formation of some common substances are given in Table 5.2. By convention, standard enthalpy for formation delta FH of an element in reference state, that is, its most stable state of aggregation, is taken as 0. Suppose you are a chemical engineer and want to know how much heat is required to decompose calcium carbonate to lime and carbon dioxide with all the substances in their standard state. CaCO3 solid gives CaO solid plus CO2 gas. Delta RH equals. Here, we can make use of standard enthalpy of formation and calculate the enthalpy change for the reaction. The following general equation can be used for the enthalpy change calculation. Delta RH equals sigma I AI delta FH products minus sigma I BI delta FH reactants, equation 5.15, where A and B represent the coefficients of the products and reactants in the balanced equation. Let us apply the above equation for decomposition of calcium carbonate. Here, coefficients A and B are 1 each. Therefore, delta RH equals delta FH equals CaO solid plus delta FH CO2 gas minus delta FH equals CaCO3 solid equals 1 into minus 635.1 kilojoules per mole plus 1 into minus 393.5 kilojoules per mole minus 1 into minus 1206.9 kilojoules per mole equals 178.3 kilojoules per mole. Thus, the decomposition of CaCO3 solid is an endothermic process, and you have to heat it for getting the desired products. D. Thermochemical equations. A balanced chemical equation together with the value of its delta RH is called a thermochemical equation. We specify the physical state along with allotropic state of the substance in an equation. For example, C2H5OH liquid plus 3O2 gas gives 2CO2 gas plus 3H2O liquid. Delta RH equals minus 1367 kilojoules per mole. The above equation describes the combustion of liquid ethanol at constant temperature and pressure. The negative sign of enthalpy change indicates that this is an exothermic reaction. It would be necessary to remember the following conventions regarding thermochemical equations. 1. The coefficients of a balanced thermochemical equation refers to the number of moles, never molecules, of reactants and products involved in the reaction. 2. The numerical value of delta RH refers to the number of moles of substances specified by an equation. Standard enthalpy change delta RH will have units as kilojoules per mole. To illustrate the concept, let us consider the calculation of heat of reaction for the following reaction. Fe2O3 solid plus 3H2 gas gives 2Fe solid plus 3H2O liquid. From the table 5.2 of standard enthalpy of formation delta FH, we find delta FH H2O liquid equals minus 285.83 kilojoules per mole. Delta FH Fe2O3 solid equals minus 824.2 kilojoules per mole. Also, delta FH FES equals 0 and delta FH H2 gas equals 0 as per convention. Then, delta FH1 equals 3 into minus 285.83 kilojoules per mole minus 1 into minus 824.2 kilojoules per mole equals minus 857.5 plus 824.2 kilojoules per mole equals minus 33.3 kilojoules per mole. Note that the coefficients used in these calculations are pure numbers which are equal to the respective stoichiometric coefficients. The unit for delta RH is kilojoules per mole, which means per mole of reaction. Once we balance the chemical equation in a particular way as above, this defines the mole of reaction. If we had balanced the equation differently, for example, half Fe2O3 solid plus 3 by 2 H2 gas gives Fe solid plus 3 by 2 H2O liquid, then this amount of reaction would be 1 mole of reaction and delta RH would be delta FH2 equals 3 by 2 into minus 285.83 kilojoules per mole minus half into minus 824.2 kilojoules per mole equals minus 428.7 plus 412.1 kilojoules per mole equals minus 16.6 kilojoules per mole equals half of delta R H1. It shows that enthalpy is an extensive quantity. 3. When a chemical equation is reversed, the value of delta RH is reversed in sign. For example, N2 gas plus 3H2 gas giving 2NH3 gas. Delta RH equals minus 91.8 kilojoules per mole. 2NH3 gas giving N2 gas plus 3H2 gas. Delta RH equals plus 91.8 kilojoules per mole. E. Hess law of constant heat summation. We know that enthalpy is a state function. Therefore, The change in enthalpy is independent of the path between initial state reactants and final state products. In other words, enthalpy change for a reaction is the same whether it occurs in one step or in a series of steps. This may be stated as follows in the form of Hess's law. If a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the overall reaction may be divided at the same temperature. Let us understand the importance of this law with the help of an example. Consider the enthalpy change for the reaction C graphite solid plus half O2 gas giving CO gas. Delta RH equals. Although CO gas is the major product, some CO2 gas is always produced in this reaction. Therefore, we cannot measure enthalpy change for the above reaction directly. However, if we can find some other reactions involving related species, it is possible to calculate the enthalpy change for the above reaction. Let us consider the following reactions. C graphite solid plus O2 gas giving CO2 gas. Delta RH equals minus 393.5 kilojoules per mole, equation 1. CO gas plus half O2 gas giving CO2 gas, delta RH equals minus 283 kilojoules per mole, equation 2. We can combine the above two reactions in such a way so as to obtain the desired reaction. To get 1 mole of CO gas on the right, we reverse equation 2. In this, heat is absorbed instead of being released. So, we change sign of delta RH value. CO2 gas gives CO gas plus half O2 gas. Delta RH equals plus 283 kilojoules per mole, equation 3. Adding equation 1 and 3, we get the desired equation C graphite solid plus half O2 gas giving CO gas, for which delta RH equals minus 393.5 plus 283 equals minus 110.5 kilojoules per mole. In general, if enthalpy of an overall reaction A to B along one route is delta RH and delta RH1, delta RH2, delta RH3, etc., representing enthalpies of reactions leading to same product B along another route, then we have delta RH equals delta RH1 plus delta RH2 plus delta RH3, etc., equation 5.16. It can be represented as given in the figure. 5.5. Enthalpies for different types of reactions. It is convenient to give name to enthalpies specifying the types of reactions. A. Standard enthalpy of combustion, symbol delta CH. Combustion reactions are exothermic in nature. These are important in industry, rocketry, and other walks of life. Standard enthalpy of combustion is defined as the enthalpy change per mole or per unit amount of a substance when it undergoes combustion and all the reactants and products being in their standard states at the specified temperature. Cooking gas in cylinders contains mostly butane, C4H10. During complete combustion of 1 mole of butane, 2658 kilojoules of heat is released. We can write the thermochemical reactions for this as C4H10 gas plus 13/2 O2 gas gives 4 CO2 gas plus 5 H2O liquid. Delta CH equals minus 2658 kilojoules per mole. Similarly, combustion of glucose gives out 2802 kilojoules per mole of heat, for which the overall equation is C6H12O6 gas plus 6O2 gas gives 6CO2 gas plus 6H2O liquid. Delta CH equals minus 2802 kilojoules per mole. Our body also generates energy from food by the same overall process as combustion, although the final products are produced after a series of complex biochemical reactions involving enzymes. Problem 5.9. The combustion of 1 mole of benzene takes place at 298 K and 1 atm. After combustion, CO2 gas and H2O liquid are produced and 3267 kilojoules of heat is liberated. Calculate the standard enthalpy of formation, delta FH of benzene. Standard enthalpies of formation of CO2 gas and H2O liquid are minus 393.5 kilojoules per mole and minus 285.83 kilojoules per mole respectively. Solution. The formation reaction of benzene is given by 6C graphite plus 3H2 gas giving C6H6 liquid. Delta FH is equation 1. The enthalpy of combustion of 1 mole of benzene is C6H6 liquid plus 15 by 2 O2 giving 6 CO2 gas plus 3 H2O liquid. Delta CH equals minus 3267 kilojoules per mole, equation 2. The enthalpy of formation of 1 mole of CO2 gas, C graphite plus O2 gas giving CO2 gas. Delta FH equals minus 393.5 kilojoules per mole, equation 3. The enthalpy of formation of 1 mole of H2O liquid is H2 gas plus half O2 gas giving H2O liquid. Delta CH equals minus 285.83 kilojoules per mole, equation 4. Multiplying equation 3 by 6 and equation 4 by 3, we get 6C graphite plus 6O2 gas giving 6 CO2 gas. Delta FH equals minus 2361 kilojoules per mole. 3H2 gas plus 3 by 2 O2 gas giving 3H2O liquid. Delta FH equals minus 857.49 kilojoules per mole. Summing up the above two equations, 6C graphite plus 3H2 gas plus 15 by 2 O2 gas gives 6 CO2 gas plus 3 H2O liquid. Delta FH equals minus 3218.49 kilojoules per mole, equation 5. Reversing equation 2, 6 CO2 gas plus 3 H2O liquid gives C6H6 liquid plus 15 by 2 O2. Delta FH equals minus 3267 kilojoules per mole, equation 6. Adding equations 5 and 6, we get 6C graphite plus 3H2 gas gives C6H6 liquid. Delta FH equals minus 48.51 kilojoules per mole, equation 7. B. Enthalpy of atomization, symbol delta AH. Consider the following example of atomization of dihydrogen. H2 gas giving 2H gas. Delta AH equals 435 kilojoules per mole. You can see that H atoms are formed by breaking H single bond H in dihydrogen. The enthalpy change in this process is known as enthalpy of atomization, delta AH. It is the enthalpy change on breaking 1 mole of bonds completely to obtain atoms in the gas phase. In case of diatomic molecules like dihydrogen given above, the enthalpy of atomization is also the bond dissociation enthalpy. The other examples of enthalpy of atomization can be CH4 gas giving C gas plus 4H gas delta AH equals 1665 kilojoules per mole. Note that the products are only atoms of C and H in gaseous phase. Now see the following reaction. Na solid giving Na gas. Delta AH equals 108.4 kilojoules per mole. In this case, the enthalpy of atomization is same as the enthalpy of sublimation. C. Bond enthalpy, symbol delta bond H. Chemical reactions involve the breaking and making of chemical bonds. Energy is required to break a bond and energy is released when a bond is formed. It is possible to relate heat of reaction to changes in energy associated with breaking and making of chemical bonds. With reference to the enthalpy changes associated with chemical bonds, two different terms are used in thermodynamics. 1. Bond dissociation enthalpy. 2. Mean bond enthalpy. Let us discuss these terms with reference to diatomic and polyatomic molecules. Diatomic molecules. Consider the following process in which the bonds in 1 mole of dihydrogen gas H2 are broken. H2 gas gives 2H gas. Delta H single bond H, capital H equals 435 kilojoules per mole. The enthalpy change involved in this process is the bond dissociation enthalpy of H single bond H bond. The bond dissociation enthalpy is the change in enthalpy when 1 mole of covalent bonds of a gaseous covalent compound is broken to form products in the gas phase. Note that it is the same as the enthalpy of atomization of dihydrogen. This is true for all diatomic molecules. For example, Cl2 gas gives 2Cl gas. Delta ClCl H equals 242 kilojoules per mole. O2 gas gives 2O gas. Delta O double bond O H equals 428 kilojoules per mole. In the case of polyatomic molecules, bond dissociation enthalpy is different for different bonds within the same molecule. Polyatomic molecules. Let us now consider a polyatomic molecule like methane CH4. The overall thermochemical equation for its atomization reaction is given below. CH4 gas gives C gas plus 4H gas. Delta AH equals 1665 kilojoules per mole. In methane, all the 4 CH bonds are identical in bond length and energy. However, the energies required to break the individual CH bonds in each successive step differ. CH4 gas gives CH3 gas plus H gas. Delta bond H equals plus 427 kilojoules per mole. CH3 gas gives CH2 gas plus H gas. Delta bond H equals plus 439 kilojoules per mole. CH2 gas gives CH gas plus H gas. Delta bond H equals plus 452 kilojoules per mole. CH gas gives C gas plus H gas. Delta bond H equals plus 347 kilojoules per mole. Therefore, CH4 gas equals C gas plus 4H gas. Delta AH equals 1665 kilojoules per mole. In such cases, we use mean bond enthalpy of C single bond H bond. For example, in CH4, delta C single bond H, capital H, is calculated as delta CH equals 1 by 4 delta AH equals 1 by 4 into 1665 kilojoules per mole equals 416 kilojoules per mole. We find that mean CH bond enthalpy in methane is 416 kilojoules per mole. It has been found that mean CH bond enthalpies differ slightly from compound to compound, as in CH3, CH2Cl, CH3NO2, etc., but it does not differ in a great deal. Using Hess's law, bond enthalpies can be calculated. Bond enthalpy values of some single and multiple bonds are given in Table 5.3. The reaction enthalpies are very important quantities as these arise from the changes that accompany the breaking of old bonds and formation of the new bonds. We can predict enthalpy of a reaction in gas phase if we know different bond enthalpies. The standard enthalpy of reaction delta RH is related to bond enthalpies of the reactants and products in gas phase reactions as delta RH equals sigma bond enthalpies reactants minus sigma bond enthalpies products, equation 5.17. If we use enthalpy of bond formation delta FH bond, which is the enthalpy change when 1 mole of a particular type of bond is formed from gaseous atom, then delta FH equals sigma delta FH bonds of products minus sigma delta FH bonds of reactants. This relationship is particularly more useful when the required values of delta FH are not available. The net enthalpy change of a reaction is the amount of energy required to break all the bonds in the reactant molecules minus the amount of energy required to break all the bonds in the product molecules. Remember that this relationship is approximate and valid when all substances, reactants and products in the reaction are in gaseous state. D. Lattice enthalpy. The lattice enthalpy of an ionic compound is the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its ions in gaseous state. Na plus Cl minus solid gives Na plus gas plus Cl minus gas. Delta lattice H equals plus 788 kilojoules per mole. Since it's impossible to determine lattice enthalpies directly by experiment, we use an indirect method where we construct an enthalpy diagram called a Born-Haber cycle, figure 5.9. Let us now calculate the lattice enthalpy of Na plus Cl minus solid by following steps given below. 1. Na solid gives Na gas, sublimation of sodium metal, delta SuBH equals 108.4 kilojoules per mole. 2. Na gas gives Na plus gas plus E minus gas, the ionization of sodium atoms, ionization enthalpy delta IH equals 496 kilojoules per mole. 3. Half Cl2 gas gives Cl gas, the dissociation of chlorine. The reaction enthalpy is half the bond dissociation enthalpy. Half delta bond H equals 121 kilojoules per mole. 4. Cl gas plus E raised to minus 1 gas gives Cl minus gas, electron gained by chlorine atoms. The electron gain enthalpy delta EGH equals minus 348.6 kilojoules per mole. You have learned about ionization enthalpy and electron gain enthalpy in Unit 3. In fact, these terms have been taken from thermodynamics. Earlier terms, ionization energy and electron affinity, were in practice in place of the above terms. See the box for justification. Ionization energy and electron affinity. Ionization energy and electron affinity are defined at absolute zero. At any other temperature, heat capacities for the reactants and the products have to be taken into account. Enthalpies of reactions for M gas giving M plus gas plus E minus for ionization. M gas plus E minus gives M minus gas for electron gain. At temperature T is delta RH equals delta RH0 plus integral 0 to T delta R Cp dt. The value of Cp for each species in the above reaction is 5 divided by 2 into R. Cv equals 3 by 2 into R. So delta R Cp equals plus 5 by 2 R for ionization. Delta R Cp equals minus 5 by 2 R for electron gain. Therefore, delta RH ionization enthalpy equals E0 ionization enthalpy plus 5 by 2 R into T. Delta RH electron gain enthalpy equals minus A electron affinity minus 5 by 2 RT. 5. Na plus gas plus Cl minus gas giving Na plus Cl minus solid. The sequence of steps is shown in figure 5.9 and is known as a Born-Haber cycle. The importance of the cycle is that the sum of the enthalpy changes round a cycle is 0. Applying Hess's law, we get delta lattice H equals 411.2 plus 108.4 plus 121 plus 496 minus 348.6. Delta lattice H equals plus 788 kilojoules for NaCl solid giving Na plus gas plus Cl minus gas. Internal energy is smaller by 2 into R into T because delta Ng equals 2 and is equal to plus 783 kilojoules per mole. Now we use the value of lattice enthalpy to calculate enthalpy of solution from the expression delta sol H equals delta lattice H plus delta HYD H. For 1 mole of NaCl solid, lattice enthalpy equals plus 788 kilojoules per mole and delta HYD H equals minus 784 kilojoules per mole from the literature. Delta SOL H equals plus 788 kilojoules per mole minus 784 kilojoules per mole equals plus 4 kilojoules per mole. The dissolution of NaCl solid is accompanied by very little heat change. E. Enthalpy of solution, symbol delta Sol H. Enthalpy of solution of a substance is the enthalpy change when 1 mole of it dissolves in a specified amount of solvent. The enthalpy of solution at infinite dilution is the enthalpy change observed on dissolving the substance in an infinite amount of solvent when the interactions between the ions or solute molecules are negligible. When an ionic compound dissolves in a solvent, the ions leave their ordered positions on the crystal lattice. These are now more free in solution. So solvation of these ions, hydration in case solvent is water, also occurs at the same time. This is shown diagrammatically for an ionic compound AB solid. See figure. The enthalpy of solution of AB solid, delta Sol H in water is therefore determined by the selective values of the lattice enthalpy, delta lattice H, and enthalpy of hydration of ions, delta HYDH, as delta SOLH equals delta lattice H plus delta HYDH. For most of the ionic compounds, delta SOLH is positive and the dissociation process is endothermic. Therefore, the solubility of most salts in water increases with rise of temperature. If the lattice enthalpy is very high, the dissolution of the compound may not take place at all. Why do so many fluorides tend to be less soluble than the corresponding chlorides? Estimates of the magnitudes of enthalpy changes may be made by using tables of bond energies enthalpies and lattice energies enthalpies. F. Enthalpy of dilution. It is known that enthalpy of solution is the enthalpy change associated with the addition of a specified amount of solute to the specified amount of solvent at a constant temperature and pressure. This argument can be applied to any solvent with slight modification. Enthalpy change for dissolving 1 mole of gaseous hydrogen chloride in 10 mole of water can be represented by the following equation. For convenience, we will use the symbol AQ for water. HCl gas plus 10AQ gives HCl 10AQ. Delta H equals minus 69.01 kilojoules per mole. Let us consider the following set of enthalpy changes. S1. HCl gas plus 25AQ gives HCl 25AQ. Delta H equals minus 72.03 kilojoules per mole. S2. HCl gas plus 40AQ gives HCl 40AQ. Delta H equals minus 72.79 kilojoules per mole. S3. HCl gas plus infinitive AQ gives HCl infinity AQ. Delta H equals minus 74.85 kilojoules per mole. The values of delta H shows general dependence of the enthalpy of solution on amount of solvent. As more and more solvent is used, the enthalpy of solution approaches a limiting value, that is, the value in infinitely dilute solution. For hydrochloric acid, this value of delta H is given above in equation S3. If we subtract the first equation, equation S1, from the second equation, equation S2, in the above set of equations, we obtain HCl 25AQ plus 15AQ giving HCl 40AQ. Delta H equals minus 72.79 minus 72.03 kilojoules per mole equals minus 0.76 kilojoules per mole. This value minus 0.76 kilojoules per mole of delta H is enthalpy of dilution. It is the heat withdrawn from the surroundings when additional solvent is added to the solution. The enthalpy of dilution of a solution is dependent on the original concentration of the solution and the amount of solvent added. 5.6. Spontaneity. The first law of thermodynamics tells us about the relationship between the heat absorbed and the work performed on or by a system. It puts no restrictions on the direction of heat flow. However, the flow of heat is unidirectional from higher temperature to lower temperature. In fact, all naturally occurring processes, whether chemical or physical, will tend to proceed spontaneously in one direction only. For example, a gas expanding to fill the available volume, burning carbon and dioxygen giving carbon dioxide. But heat will not flow from colder body to warmer body on its own. The gas in a container will not spontaneously contract into one corner, or carbon dioxide will not form carbon and dioxygen spontaneously. These and many other spontaneously occurring changes show unidirectional change. We may ask, what is the driving force of spontaneously occurring changes? What determines the direction of a spontaneous change? In this section, we shall establish some criterion for these processes, whether these will take place or not. Let us first understand what do we mean by spontaneous reaction or change. You may think by your common observation that spontaneous reaction is one which occurs immediately when contact is made between the reactants. Take the case of combination of hydrogen and oxygen. These gases may be mixed at room temperature and left for many years without observing any perceptible change. Although the reaction is taking place between them, it is at an extremely slow rate. It is still called spontaneous reaction. So, spontaneity means having the potential to proceed without the assistance of external agency. However, it does not tell about the rate of the reaction or process. Another aspect of spontaneous reaction or process, as we see, is that these cannot reverse their direction on their own. We may summarize it as follows. A spontaneous process is an irreversible process and may only be reversed by some external agency. A. Is decrease in enthalpy a criterion for spontaneity? If we examine the phenomenon like flow of water downhill or fall of a stone onto the ground, we find that there is a net decrease in potential energy in the direction of change. By analogy, we may be tempted to state that a chemical reaction is spontaneous in a given direction because decrease in energy has taken place, as in the case of exothermic reactions. For example, half N2 gas plus minus H2 gas equals NH3 gas. Delta RH equals minus 46.1 kilojoules per mole. Half H2 gas plus half Cl2 gas equals HCl gas. Delta RH equals minus 92.32 kilojoules per mole. H2 gas plus half O2 gas giving H2O liquid. Delta RH equals minus 285.8 kilojoules per mole. The decrease in enthalpy in passing from reactants to products may be shown for any exothermic reaction on an enthalpy diagram as shown in figure 5.10a. Thus, the postulate that driving force for a chemical reaction may be due to decrease in energy sounds reasonable as the basis of evidence so far. Now let us examine the following reactions. Half N2 gas plus O2 gas giving NO2 gas. delta RH equals plus 33.2 kilojoules per mole. C graphite solid plus 2S liquid giving CS2 liquid. Delta RH equals plus 128.5 kilojoules per mole. These reactions, though endothermic, are spontaneous. The increase in enthalpy may be represented on an enthalpy diagram as shown in figure 5.10b. Therefore, it becomes obvious that while decrease in enthalpy may be a contributory factor for spontaneity, but it is not true for all cases. B. Entropy and spontaneity. Then what drives the spontaneous process in a given direction? Let us examine such a case in which delta H equals 0, that is, there is no change in enthalpy but still the process is spontaneous. Let us consider diffusion of two gases into each other in a closed container which is isolated from the surroundings as shown in figure 5.11. The two gases, say gas A and gas B, are represented by black dots and white dots respectively and separated by a movable partition, figure 5.11a. When the partition is withdrawn, figure 5.11b, the gases begin to diffuse into each other and after a period of time, diffusion will be complete. Let us examine the process. Before partition, if we were to pick up the gas molecules from left container, we would be sure that these will be the molecules of gas A, and similarly, if we were to pick up the gas molecules from right container, we would be sure that these will be the molecules of gas B. But if we were to pick up molecules from container when partition is removed, we are not sure whether the molecules picked are of gas A or gas B. We say that the system has become less predictable or more chaotic. We may now formulate another postulate. In an isolated system, there is always a tendency for the system's energy to become more disordered or chaotic, and this could be a criterion for spontaneous change. At this point, we introduce another thermodynamic function, entropy, denoted by capital S. The above-mentioned disorder is the manifestation of entropy. To form a mental picture, one can think of entropy as a measure of the degree of randomness or disorder in the system. The greater the disorder in an isolated system, the higher is the entropy. As far as a chemical reaction is concerned, this entropy change can be attributed to rearrangement of atoms or ions from one pattern in the reactants to another in the products. If the structure of the products is very much disordered than that of the reactants, there will be a resultant increase in entropy. The change in entropy accompanying a chemical reaction may be estimated qualitatively by a consideration of the structures of the species taking part in the reaction. Decrease of regularity in structure would mean increase in entropy. For a given substance, the crystalline solid state is the state of lowest entropy, most ordered. The gaseous state is the state of highest entropy. Now let us try to quantify entropy. One way to calculate the degree of disorder or chaotic distribution of energy among molecules would be through statistical method which is beyond the scope of this treatment. Other way would be to relate this process to the heat involved in a process, which would make entropy a thermodynamic concept. Entropy, like any other thermodynamic property such as internal energy U and enthalpy H, is a state function and delta S is independent of path. Whenever heat is added to the system, it increases molecular motions, causing increased randomness in the system. Thus, heat Q has randomizing influence on the system. Can we then equate delta S with Q? Wait, Experience suggests us that the distribution of heat also depends on the temperature at which heat is added to the system. A system at higher temperature has greater randomness in it than one at lower temperature. Thus, temperature is the measure of average chaotic motion of particles in the system. Heat added to a system at lower temperature causes greater randomness than when the same quantity of heat is added to it at higher temperature. This suggests that the entropy change is inversely proportional to the temperature. Delta S is related with Q and capital T for a reversible reaction as delta S equals Q ReV divided by capital T. Equation 5.18. The total entropy change delta S total for the system and surroundings of a spontaneous process is given by delta S total equals delta S system plus delta S SURR greater than 0. Equation 5.19. When a system is in equilibrium, the entropy is maximum and the change in entropy delta S equals 0. We can say that entropy for a spontaneous process increases till it reaches maximum, and at equilibrium the change in entropy is 0. Since entropy is a state property, we can calculate the change in entropy of a reversible process by delta S sys equals Q sys, ReV divided by T. We find that both for reversible and irreversible expansion for an ideal gas under isothermal conditions, delta U equals 0, but delta S total, that is, delta S sys plus delta S SURR is not 0 for irreversible process. Thus, delta U does not discriminate between reversible and irreversible process, whereas delta S does. Problem 5.10. Predict in which of the following entropy increases or decreases. 1. A liquid crystallizes into a solid. 2. Temperature of a crystalline solid is raised from 0 K to 115 K. 3. 2NaHCO3 solid gives Na2CO3 solid plus CO2 gas plus H2O gas. 4. H2 gas gives 2H gas. Solution. 1. After freezing, the molecules attain an ordered state and therefore entropy decreases. 2. At 0 K, the constituent particles are static and entropy is minimum. If temperature is raised to 115 K, these begin to move and oscillate about their equilibrium positions in the lattice, and system becomes more disordered, therefore entropy increases. 3. Reactant NaHCO3 is a solid and it has low entropy. Among products, there are 1 solid and 2 gases. Therefore, the products represent a condition of higher entropy. 4. Here, 1 molecule gives 2 atoms, that is, number of particles increases, leading to more disordered state. 2 moles of H atoms have higher entropy than 1 mole of dihydrogen molecule. Problem 5.11. For oxidation of iron, 4Fe solid plus 3O2 gas gives 2Fe2O3 solid. Entropy change is minus 549.4 joules per K per mole at 298 K. In spite of negative entropy change of this reaction, why is the reaction spontaneous? Delta RH for this reaction is minus 1648 into 10 raised to 3 joules per mole. Solution. One decides the spontaneity of a reaction by considering delta S total, delta S SYS plus delta S SURR. For calculating delta S SURR, we have to consider the heat absorbed by the surroundings, which is equal to minus delta RH. At temperature T, entropy change of the surroundings is delta S SURR equals minus delta RH divided by T at constant pressure equals minus 1648 into 10 raised to 3 joules per mole divided by 298 K equals 5530 joules per K per mole. Thus, total entropy change for this reaction delta R S total equals 5530 joules per K per mole plus minus 549.4 joules per K per mole equals 4980.6 joules per K per mole. This shows that the above reaction is spontaneous. C. Gibbs energy and spontaneity. We have seen that for a system, it is the total entropy change delta S total which decides the spontaneity of the process. But most of the chemical reactions fall into the category of either closed systems or open systems. Therefore, for most of the chemical reactions, there are changes in both enthalpy and entropy. It is clear from the discussion in previous sections that neither decrease in enthalpy nor increase in entropy alone can determine the direction of spontaneous change for these systems. For this purpose, we define a new thermodynamic function, the Gibbs energy or Gibbs function G, as G equals H minus T into S. Equation 5.20. Gibbs function G is an extensive property and a state function. The change in Gibbs energy for the system delta G SYS can be written as delta G SYS equals delta H SYS minus T into delta S SYS minus S SYS into delta T. At constant temperature, delta T equals 0. Delta G SYS equals delta H SYS minus T into delta S SYS. Usually the subscript system is dropped and we simply write this equation as delta G equals delta H minus T into delta S. Equation 5.21. Thus, Gibbs energy change equals enthalpy change minus temperature into entropy change and is referred to as the Gibbs equation, one of the most important equations in chemistry. Here, we have considered both terms together for spontaneity. Energy in terms of delta H and entropy delta S, a measure of disorder as indicated earlier. Dimensionally, if we analyze, we find that delta G has units of energy because both delta H and the T into delta S are energy terms since T into delta S equals K into J divided by K equals J, joules. Now let us consider how delta G is related to reaction spontaneity. We know delta S total equals delta S SYS plus delta S SURR. If the system is in thermal equilibrium with the surrounding, then the temperature of the surrounding is same as that of the system. Also, increase in enthalpy of the surrounding is equal to decrease in the enthalpy of the system. Therefore, entropy change of surroundings delta S SURR equals delta H SURR divided by T equals minus delta H SYS divided by T. Delta S total equals delta S SYS plus minus delta H SYS divided by T. Rearranging the above equation, T into delta S total equals T into delta S SYS minus delta H SYS. For spontaneous process, delta S total greater than 0. So, T into delta S SYS minus delta H SYS greater than 0. That is, minus delta H SYS minus T into delta S SYS greater than 0. Using equation 5.21, the above equation can be written as minus delta G greater than 0. Delta G equals delta H minus T into delta S less than 0. Equation 5.22. Delta H SYS is the enthalpy change of a reaction. T into delta S SYS is the energy which is not available to do useful work. So, delta G is the net energy available to do useful work and is thus a measure of the free energy. For this reason, it is also known as the free energy of the reaction. Delta G gives a criteria for spontaneity at constant pressure and temperature. 1. If delta G is negative, less than 0, the process is spontaneous. 2. If delta G is positive, greater than 0, the process is non-spontaneous. Note: if a reaction has positive enthalpy change and positive entropy change, it can be spontaneous when T into delta S is large enough to outweigh delta H. This can happen in two ways. A. The positive entropy change of the system can be small, in which case T must be large. B. The positive entropy change of the system can be large, in which case T may be small. The former is one of the reasons why reactions are often carried out at high temperature. Table 5.4 summarizes the effect of temperature on spontaneity of reactions. D. Entropy and second law of thermodynamics. We know that for an isolated system, the change in energy remains constant. Therefore, increase in entropy in such systems is the natural direction of a spontaneous change. This, in fact, is the second law of thermodynamics. Like first law of thermodynamics, second law can also be stated in several ways. The second law of thermodynamics explains why spontaneous exothermic reactions are so common. In exothermic reactions, heat released by the reaction increases the disorder of the surroundings, and overall entropy change is positive, which makes the reaction spontaneous. E. Absolute entropy and third law of thermodynamics. Molecules of a substance may move in a straight line in any direction. They may spin like a top, and the bonds in the molecules may stretch and compress. These motions of the molecule are called translational, rotational, and vibrational motion, respectively. When temperature of the system rises, these motions become more vigorous and entropy increases. On the other hand, when temperature is lowered, the entropy decreases. The entropy of any pure crystalline substance approaches zero as the temperature approaches absolute zero. This is called third law of thermodynamics. This is so because there is perfect order in a crystal at absolute zero. The statement is confined to pure crystalline solids because theoretical arguments and practical evidences have shown that entropy of solutions and supercooled liquids is not zero at 0K. The importance of the third law lies in the fact that it permits the calculation of absolute values of entropy of pure substance from thermal data alone. For a pure substance, this can be done by summing QRAV divided by T increments from 0K to 298K. Standard entropies can be used to calculate standard entropy changes by a Hess law type of calculation. 5.7 Gibbs energy change and equilibrium. We have seen how a knowledge of the sign and magnitude of the free energy change of a chemical reaction allows 1. Prediction of the spontaneity of chemical reaction. 2. Prediction of the useful work that could be extracted from it. So far, we have considered free energy changes in irreversible reactions. Let us now examine the free energy changes in reversible reactions. Reversible, under strict thermodynamic sense, is a special way of carrying out a process such that system is at all times in perfect equilibrium with its surroundings. When applied to a chemical reaction, the term reversible indicates that a given reaction can proceed in either direction simultaneously so that a dynamic equilibrium is set up. This means that the reactions in both the directions should proceed with a decrease in free energy, which seems impossible. It is possible only if, at equilibrium, the free energy of the system is minimum. If it is not, the system would spontaneously change to configuration of lower free energy. So the criterion for equilibrium, A plus B gives C plus D and reverse, is delta Rg equals 0. Gibbs energy for a reaction in which all reactants and products are in standard state, delta Rg is related to the equilibrium constant of the reaction as follows. 0 equals delta Rg plus R into T ln K, or delta Rg equals minus R into T ln K, or delta Rg equals minus 2.303 R into T into log K, equation 5.23. We also know that delta Rg equals delta Rh minus T into delta Rs equals minus RT ln K, equation 5.24. For strongly endothermic reactions, the value of delta Rh may be large and positive. In such a case, value of K will be much smaller than 1 and the reaction is unlikely to form much product. In case of exothermic reactions, delta Rh is large and negative, and delta Rg is likely to be large and negative too. In such cases, K will be much larger than 1. We may expect strongly exothermic reactions to have a large K and hence can go to near completion. Delta Rg also depends upon delta Rs if the changes in the entropy of reaction is also taken into account. The value of K or extent of chemical reaction will also be affected depending upon whether delta Rs is positive or negative. Using equation 5.24, 1. It is possible to obtain an estimate of delta G from the measurement of delta H and delta S and then calculate K at any temperature for economic yields of the products. 2. If K is measured directly in the laboratory, value of delta G at any other temperature can be calculated. Problem 5.12. Calculate delta Rg for conversion of oxygen to ozone. 3/2 O2 gas gives O3 gas at 298 K if Kp for this conversion is 2.47 into 10 raised to minus 29. Solution. We know delta Rg equals minus 2.303 RT log Kp and R is equal to 8.314 joules per K per mole. Therefore, delta Rg equals minus 2.303 into 8.314 joules per K per mole into 298 K into log 2.47 into 10 raised to minus 29 equals 163,000 joules per mole equals 163 kilojoules per mole. Problem 5.13. Find out the value of equilibrium constant for the following reaction at 298 K. 2NH3 gas plus CO2 gas gives NH2CONH2AQ plus H2O liquid. Standard Gibbs energy change delta Rg at the given temperature is minus 13.6 kilojoules per mole. Solution. We know log K equals minus delta Rg divided by 2.303 R into T equals minus 13.6 into 10 raised to 3 joules per mole divided by 2.303 into 8.314 joules per K per mole into 298 K equals 2.38. Hence, K equals anti-log 2.38 equals 2.4 into 10 raised to 2. Problem 5.14. At 60 degrees Celsius, dinitrogen tetroxide is 50% dissociated. Calculate the standard free energy change at this temperature and at 1 atmosphere. Solution. N2O4 gas gives 2NO2 gas. If N2O4 is 50% dissociated, the mole fraction of both the substances is given by chi N2O4 equals 1 minus 0.5 divided by 1 plus 0.5. Chi NO2 equals 2 into 0.5 divided by 1 plus 0.5. P N2O4 equals 0.5 divided by 1.5 into 1 atm. P NO2 equals 1 divided by 1.5 into 1 atm. The equilibrium constant Kp is given by Kp equals P NO2 raised to 2 divided by P N2O4 equals 1.5 divided by 1.5 raised to 2 into 0.5 equals 1.33 atm. Since delta Rg equals minus RT ln Kp, delta Rg equals minus 8.314 joules per K per mole into 333 K into 2.303 into 0.1239 equals minus 763.8 kilojoules per mole. Summary. Thermodynamics deals with energy changes in chemical or physical processes and enables us to study these changes quantitatively and to make useful predictions. For these purposes, we divide the universe into the system and the surroundings. Chemical or physical processes lead to evolution or absorption of heat Q, part of which may be converted into work W. These quantities are related through the first law of thermodynamics via delta U equals Q plus W. Delta U, change in internal energy, depends on initial and final states only and is a state function, whereas Q and W depend on the path and are not the state functions. We know sign conventions of Q and W by giving the positive sign to these quantities When these are added to the system, we can measure the transfer of heat from one system to another, which causes the change in temperature. The magnitude of rise in temperature depends on the heat capacity C of a substance. Therefore, heat absorbed or evolved is Q is equal to C into delta T. Work can be measured by W is equal to minus PEX into delta V in case of expansion of gases. Under reversible process, we can put PEX equals P for infinitesimal changes in the volume, making WREV equals minus P into D into V. In this condition, we can use gas equation P into V is equal to N into R into T. At constant volume W is equal to 0, then delta U equals QV, heat transfer at constant volume. But in study of chemical reactions, we usually have constant pressure. We define another state function enthalpy. Enthalpy change delta H equals delta U plus delta Ng into RT can be found directly from the heat changes at constant pressure delta H equals Qp. There are varieties of enthalpy changes. Changes of phase such as melting, vaporization, and sublimation usually occur at constant temperature and be characterized by enthalpy changes which are always positive. Enthalpy of formation, combustion, and other enthalpy changes can be calculated using Hess law. Enthalpy change for chemical reactions can be determined by delta RH equals sigma F of AI into delta F H products minus sigma I of Bi into delta F H reactions, and in gaseous states by delta RH equals sigma bond enthalpies of the reactants minus sigma bond enthalpies of the products. First law of thermodynamics does not guide us about the direction of chemical reactions. That is, what is the driving force of a chemical reaction? For isolated systems, delta U equals 0. We define another state function S, entropy, for this purpose. Entropy is a measure of disorder or randomness. For a spontaneous change, total entropy change is positive. Therefore, for an isolated system, delta U equals 0, delta S greater than 0, so entropy change distinguishes a spontaneous change while energy change does not. Entropy changes can be measured by the equation delta S equals QREV divided by T for a reversible process. QREV divided by T is independent of path. Chemical reactions are generally carried at constant pressure, so we define another state function Gibbs energy G, which is related to entropy and enthalpy changes of the system by the equation delta Rg equals delta Rh minus T into delta Rs. For spontaneous change, delta G SYS less than 0 and at equilibrium, delta G SYS equals 0. Standard Gibbs energy change is related to equilibrium constant by delta Rg equals minus R into T ln K. K can be calculated from this equation if we know delta Rg, which can be found from delta Rg equals delta Rh minus T into delta Rs. Temperature is an important factor in the equation. Many reactions which are non-spontaneous at low temperature are made spontaneous at high temperature for systems having positive entropy of reaction. Exercises 5.1. Choose the correct answer. A thermodynamic state function is a quantity 1. Used to determine heat changes. 2. Whose value is independent of path. 3. Used to determine pressure volume work. 4. Whose value depends on temperature only. 5.2. For the process to occur under adiabatic conditions, the correct condition is 1. Delta T equals 0. 2. Delta P equals 0. 3. Q equals 0. 4. W equals 0. 5.3. The enthalpies of all elements in their standard states are 1. Unity, 2. 0, 3. Less than 0, 4. Different for each element. 5.4. Delta U of combustion of methane is minus X kJ per mole. The value of delta H is 1. Equals delta U, 2. Greater than delta U, 3. Less than delta U, 4. Equals 0. 5.5. The enthalpy of combustion of methane, graphite and dihydrogen at 298 K are minus 890.3 kilojoules per mole, minus 393.5 kilojoules per mole and minus 285.8 kilojoules per mole respectively. Enthalpy of formation of CH4 gas will be 1. Minus 74.8 kilojoules per mole, 2. Minus 52.27 kilojoules per mole, 3. Plus 74.8 kilojoules per mole, 4. Plus 52.26 kilojoules per mole. 5.6. A reaction A plus B gives C plus D plus Q is found to have a positive entropy change. The reaction will be 1. Possible at high temperature, 2. Possible only at low temperature, 3. Not possible at any temperature, 5. Possible at any temperature. 5.7. In a process, 701 joules of heat is absorbed by a system and 394 joules of work is done by the system. What is the change in internal energy for the process? 5.8. The reaction of cyanamide NH2CN solid with dioxygen was carried out in a bomb calorimeter and delta U was found to be minus 742.7 kilojoules per mole at 298 K. Calculate enthalpy change for the reaction at 298 K. NH2CN gas plus 3/2 O2 gas gives N2 gas plus CO2 gas plus H2O liquid. 5.9. Calculate the number of kJ of heat necessary to raise the temperature of 60 grams of aluminum from 35 degrees Celsius to 55 degrees Celsius. Molar heat capacity of aluminum is 24 joules per mole per K. 5.10. Calculate the enthalpy change on freezing of 1 mole of water at 10 degrees Celsius to ice at minus 10 degrees Celsius. Delta FUSH equals 6.03 kilojoules per mole at 0 degrees Celsius. Cp of H2O liquid equals 75.3 joules per mole per K. Cp of H2O solid equals 36.8 joules per mole per K. 5.11. Enthalpy of combustion of carbon to CO2 is minus 393.5 kilojoules per mole. Calculate the heat released upon formation of 35.2 grams of CO2 from carbon and dioxygen gas. 5.12. Enthalpies of formation of CO gas, CO2 gas, N2O gas and N2O4 gas are minus 110, minus 393, 81 and 9.7 kilojoules per mole respectively. Find the value of delta RH for the reaction. N2O4 gas plus 3CO gas gives N2O gas plus 3CO2 gas. 5.13. Given N2 gas plus 3H2 gas gives 2NH3 gas, delta RH equals minus 92.4 kilojoules per mole. What is the standard enthalpy of formation of NH3 gas? 5.14. Calculate the standard enthalpy of formation of CH3OH liquid from the following data. CH3OH liquid plus 3/2 O2 gas gives CO2 gas plus 2H2O liquid. Delta RH equals minus 726 kilojoules per mole. C graphite plus O2 gas gives CO2 gas. Delta CH equals minus 393 kilojoules per mole. H2 gas plus half O2 gas gives H2O liquid. Delta FH equals minus 286 kilojoules per mole. 5.15. Calculate the enthalpy change for the process CCl4 gas gives C gas plus 4Cl gas and calculate bond enthalpy of C single bond Cl in CCl4 gas. Delta VAPH of CCl4 equals 30.5 kilojoules per mole. Delta FH of CCl4 equals minus 135.5 kilojoules per mole. Delta AH of C equals 715 kilojoules per mole, where delta AH is enthalpy of atomization. Delta AH of Cl2 equals 242 kilojoules per mole. 5.16. For an isolated system, delta U equals 0. What will be delta S? 5.17. For the reaction at 298 K, 2A plus B gives C, delta H equals 400 kilojoules per mole and delta S equals 0.2 kilojoules per K per mole. At what temperature will the reaction become spontaneous, considering delta H and delta S to be constant over the temperature range? 5.18. For the reaction 2Cl gas gives Cl2 gas, what are the signs of delta H and delta S? 5.19. For the reaction 2A gas plus B gas giving 2D gas, delta U equals minus 10.5 kilojoules and delta S equals minus 44.1 J per K. Calculate delta G for the reaction and predict whether the reaction may occur spontaneously. 5.20. The equilibrium constant for a reaction is 10. What will be the value of delta G? R equals 8.314 J per K per mole. T equals 300 K. 5.21. Comment on the thermodynamic stability of NO gas given half N2 gas plus half O2 gas gives NO gas. Delta RH equals 90 kJ per mole. NO gas plus half O2 gas gives NO2 gas. Delta RH equals minus 74 kilojoules per mole. 5.22. Calculate the entropy change in surroundings when 1 mole of H2O liquid is formed under standard conditions. Delta FH equals minus 286 kilojoules per mole.